Today I'll be speaking about using RLN in a peer-to-peer network, and I'll be talking about the dimensions of using RLN, the limitations, and how we can improve. So first, I'm sure Razul went over this in detail, but why do you need RLN? And I think the answer boils down to just one word, and that is spam. I can identify spam as two layers. So at first, you have the network layer spam and you have application layer spam. Now, identifying application layer spam is a real difficult uh, process because it's mostly community controlled. But what we can do is prevent network layer spam. Let's talk about how traditional Web 2 companies apply this. And it is, again, two things. One is IP address logging and KYC logging. So for IP address logging, if a Web 2 service detects too many requests coming from a specific IP address, they throttle them or they just ban them outright. And for KYC logging, if they receive too many requests from a given user's account, they just ban the user's account. Uh, but when we're talking about anonymous networks, we have a big problem. We cannot identify the spam. Because as Rasul said, you can cycle your IP addresses, you can use a mixnet, and there are no user identities. So this is why we need RLN to do this. Let's talk about where we use RLN, and it is Waku. Waku can be identified as a family of protocols for private, secure, decentralized, and peer-to-peer communication. There is a Waku family of protocols as well as a Waku network, which is an opinionated version of them. So what is Waku RLN Relay? Since Waku is built upon lib peer-to-peer, Waku RLN Relay is just a gossip sub validator, which takes in an RLN proof attached to a message. So we also validate on a few other fields, which is your epoch. So if an epoch is more than 10 seconds old, then we just reject that message altogether. And we also have an RLN identifier, which uniquely identifies your application. So if there are multiple RLN applications, they each have a unique RLN identifier, which is to prevent replay attacks for different applications. And we also have a nullifier check, which essentially detects that spam has occurred. Before I get into how Waku uses RLN, let me talk briefly about the project structure so everyone's on the same page. Up top, we have SORCOM RLN built by PSC, which exports the Z key, verifier, and the circuit, which we then ingest into ZeroKit. And we have a Rust crate, which is exported, which exports two things: a public API, which can be used in other Rust applications, and an FFI API, which is exposed to any language that can consume the C FFI API. So we have a public CLI tool, which you can use to generate RLN proofs, along with the implementations in Waku and GoWaku. Secondly, we have the RLN contract, which exports an abstract contract which applications can use to have custom validation for their registration process. So registering to an RLN contract is mostly restricted to financial stake, but with so many applications, decentralized applications, you can do pretty interesting things with this, like restricting access to the RLN membership set with an NFT or a soulbound token or any sort of ERC20. So again, we consume these two contracts in Waku and GoWaku. So let me show you a simulation of what the Waku network looks like without RLN. And so here we have a bunch of Waku nodes and we have a bad actor. Let's call the bad actor Alice. So you can see we're propagating messages, Alice starts spamming, and yes, these Waku nodes die. Let us go through the RLN registration process so that I can explain what Waku looks like with RLN. So here we have Alice. Again, she is the bad actor. She generates identity credentials, and she submits them to the membership contract with some stake. And then her commitment is added to the Merkle tree here. So Alice has now registered to the RLN membership set, and let's see what she can do when the Waku network has a few nodes with RLN enabled. The Waku nodes with dotted lines are those which have RLN enabled. So you can see she tries doing the same thing again. The Waku nodes verify the proof and forward it. And when they detect that they have too many signals per epoch, they drop the message altogether. And you can see few nodes have died, but the rest of the network is secure. So at this point, you may ask, why don't we just use semaphore and use semaphore in Waku? The problem with semaphore is while it does have membership inclusion, it lacks a bad incentive or disincentive rather for bad actors. So we want to remove bad actors from the membership set whenever we can, and that's why we use RLN through the interpolation mechanism that Rasul explained. So now let's look at Waku with RLN relay and slashing enabled. It's the same process. The proofs are verified and propagated, and then we can see that the messages have been dropped. In the next step, we see that the Waku node can slash with a proof that basically says that they know the identity of a given node. When they do this, they get this slashed user stake, that is Alice's stake, and Alice is removed from the membership set. Now you can ask me now, talk is cheap. How does it perform? Well, the simulations show it for themselves. We have a proof generation time of 150 milliseconds, and additionally, proof verification time of around 15 milliseconds. Here is quite an interesting graph. As you can see, there is a node which submits around 3,000 messages per minute, which is much greater than the epoch limit. And you can see at that instance, all the Waku nodes have dropped that Pure's connection. So they've all been protected from spam. What's next? So we have quite a few things in the pipeline. One is we want to optimize proof generation and verification time in ZeroKit. As part of this process, we've also tried to identify alternative hash functions than Poseidon that we can use. At ZK-Hack, we worked on reinforced concrete. We're still auditing it, but it is a viable replacement for Poseidon. We also want to move to a different proof system like KZG RLN that Rasul described. And we want to experiment with a tree depth of 32, which offers us like 1 billion commitments, and compare the performance with the existing depth, which is 20. Of course, we want to optimize gas usage of smart contracts and conduct audits on them. And we want to experiment with multi-epoch signaling. Something that we've noticed in Waku is users want to be able to send 1 message per second, but we also want to restrict them to use only 1,000 messages per day. And the problem with this is we have only 1 epoch that goes into the circuit, and we just have to work with different frames to see how we can do that. Finally, here, you can come join us at VAC so that you can help us build RLN for anonymous networks and potentially even for validator privacy. There is a dev guide for RLN Relay, so you can start bootstrapping your application with Waku and RLN Relay. That's it. Thank you.
Amazing. Have time for questions.
Yeah. Any questions? Yeah.
Hello, nice presentation. How many users Waku has, and how have you been able to scale the network itself more than RLN?
Good question. So about the Waku network scaling itself. So we've implemented sharding, which allows Waku nodes to connect to their own shard. Technically, it's different pub subtopics in Gossip Sub. Now, what this allows us to do is have much more throughput on the network and also have Waku nodes accepting information or messages from only the pub subtopics that they're interested in. Yeah, that could be something interesting we could do about incentivization for different pub subtopics, because of course mesh forming is a very big issue when you try to shard a Gossip Sub network.
Thank you.
Any other questions? Okay, thank you.
Big round of applause. Thank you, Aaryamann.